Good morning. Let's briefly review Chapter 4. That is the assignment for this week. Chapter 4, the title is Annuity with Different Payment and Conversion Period. So 4.1 Introduction. In Chapter 3, we study annuity with regularly spaced payment, in which the payment period and interest period coincide. In this chapter, we again study annuity with regularly spaced payment, and a variety of payment patterns. So we drop the requirement that the interest payment and payment period coincide. Okay, so interest period, we're talking about, do you compound monthly, do you compound quarterly, compound annually? Those are the interest period. The payment period, are we making monthly payment, 2 months payment, half year payment? So in Chapter 3, the payment period and the interest period are the same. They're either both monthly or both annually. In Chapter 4, they could be different. You could have interest compounded continuously, but your payment is being paid annually. Or you could have a payment that's paid every half year, every 6 months, but your interest may be compounded annually. So there's different type of conversion. So starting 4.1, we try to derive the formula. So in 4.2, level annuity with payment. So the payment are the same amount, but the payment is less frequently than the interest period. So suppose the interest period is annually, you compound annually, but you're paying it every month. That will be this less frequent than the interest period. That means suppose you compound annually, but you're paying it every other year. That will be the situation. So we're gonna try to devise a formula. Here we're using the n, the letter n, number n, representing number of interest period. The interest period is more than the payment number, than the number of payments, because we're paying less frequently than the interest period. So let's assume that the number of payment is K. So number of payment is K. Every payment in the study of annuity, we're assuming each payment is $1. The length, so that means the number of payment is R. So N equal to R times K. K is the length of the payment period, but R is the number of the payment period. So N equal to R times K. So at time K, you make payment of $1. At time 2K, another $1. Times 3K, another $1. So overall, in the time from 0 to N, we're making R dollar total payment, total number, dollar amount is R dollar, but they're being paid at different time period. So that means the final total is less than R dollar, because some of the money has to be discounted if you have the payment before the time end. We're talking about time end value. So you can see this is a timeline. The top one is the payment amount. The bottom one is a time point. Okay. So basically, try to enlarge this. So let's look at an example just to derive the formula. Suppose you have a you want to pay $4,000. Pay $4,000 at the end of each 6 months for 6 years. Use compound interest at a nominal monthly interest rate of 3%. So in this case, the interest is monthly interest. It's a nominal interest. So the nominal interest rate is 3%. 3% divided by 12. Every month there's a 0.025. I mean 0.03 divided by 12 is 0.025. that is a monthly interest rate, and this month is compound monthly in this case because it's a nominal monthly interest. So the interest period is shorter since it's a monthly. The payment period is 6 months, so we are paying less frequently than the interest period. The question is, what is the value of the reward at the end of at the time of the announcement? Okay, so this is reward at the time of the announcement. When was the announcement? 6 months before the first. Okay, so that is a time zero value. So this question is calculating the present value of a annuity. $4,000 has to multiply by the annuity formula A12I. Now this I is the interest, monthly interest. So this I, it actually should be the annuity interest. That should be the 6 months interest. So here we calculate the I is a 6 months interest. Each month the growth factor is 1 plus 0.3 over 12. We let it grow for 6 months and then minus 1 to get the interest rate. The 6 months interest rate is a capital I. Then the number payment for 6 years, if we make payments every 6 months, so that will be half year a payment, and in 1 year there's 2 payment, 2 times 6. In 6 years there should be 12 payment overall. So number payment is 12, interest rate is I. That allows us to calculate the total value at time 0. And again, if you want to calculate the total value at time 6 years later, you have to multiply the annual interest rate, which is this interest rate, the 1 plus 0.03012 to the power 12 minus 1 to the power 12. Yeah, that will be the one you multiply. You multiply the accumulation function to get the time 6 value. But right now the question is calculating the present value at time 0. So this one is our first example. We're trying to use this to derive the formula. And that is the ARI. And here we have the A12I, and that's the one we try to derive a way to calculate this. And this calculation actually is calculated by, we have a formula for A12I, and that is the 1 minus the deduction rate to the power 12 over I. But see, I is this. So you can write this I. The I is this. This looks very much like the accumulation function -1. So we try to devise a way to calculate this. So ARI, see, this is according to the A formula, the annuity formula. Now the denominator I, right here, the capital I, the denominator I, is calculated using the nominal interest rate and divided by 12. And so this function and is coincide with what we're writing here. And then if you divide the numerator and denominator by I, they are matching the formula that we had earlier for the A formula and S formula. Again, the A represent present value for the annuity, S represent the future value of the annuity or expiration value of the annuity. And this is all for a sequence of payment of $1 that is from chapter 3. So then this gives us a way to look at how are we going to calculate the annuity if the payment period is shorter than the interest period. So that's 4.2.4, and that's going to be our first formula. Well, 4.2.3, that's the A formula. Now, if you multiply this equation by 1 plus I to the power n, you are getting the formula for the future value, and that's the 4.2.4. So both of these formula have the denominator SK, and that is because the n is number of interest period. yeah, number in interest period. In this case, n equal to every month is 12 times 6, and equal to 72 in this question. N is number of interest period, and K is the length of payment period. N over K is R, and R is the number of payment period. So you can kind of think of it as N equal to S times K, R times K. So S equal to N over K. So in a way, in this calculation of the annuity, it involves some of the analysis between the relation of N, R, and K. And that's kind of how I try to connect the formula together. So, so fact 4.2.5 summarizes the present value is AN over SK, and then the future value is SN over SK. All right. Similarly, we can look at what we have is annuity immediate. We can also look at annuity due. If you have N payments, not N payment, R payment, but this payment are annuity due. So you have $1 payment at time 0, time K, time 2K, and time R minus 1 time K. And there's no payment, assuming the final time is at time N, and there's no payment there because it's annuity due. You pay the payment at the beginning of the payment period. The length of the payment period is K. In this case, it is similar to, if you want to find the time 0 value, it is similar to the annuity immediate, but you move the time period one period forward, I think. So it's like the annuity immediate formula if you're calculating the time value at time 1 instead of time 0. So if you have time 0, you follow what we just had. All right. Now, if you are calculating time 1 and you have to take the time 0 value multiplied by 1 plus I, right? You let it grow for one time period, one payment period. And that gives us the opportunity to apply what we already have and come up with a new formula. So for annuity due, the present value is AN over AK. Then the future value at time N, that is Sn over AK. So one of the ideas that we can get for annuity due, the denominator is AK, but for annuity immediate, which we get from here, the denominator is SK instead of AK. So I guess that's the part. All right. Because for a payment period, as one is the growth factor from time 0 to time K. If you multiply that growth factor to your function, you're changing the future value of the one time period from 0 to K, from SK to AK, because the factor that you multiply to the numerator cancel the denominator, cancel one of the factor in the denominator SK. All right, so we're trying to connect them, and let's see if the formula works. Actually, I've been actually when I was calculating, I really try to remember the formula. What I usually do is to look at the timeline and find the time value of it without rely too much on the formula. All right, so this is an example. Let's see if we can apply the formula. Josh makes annual beginning of the year contribution of 3,000 to a retirement account. The account has a nominal interest rate of 4.8%. So here, convertible monthly. So right here, the account have a nominal interest rate of 4.8 convertible monthly. That means the interest period is 1 month. It's monthly, but the payment period is annual payment. and it's being paid at the beginning of the year. So it's annuity due. The amount is 3,000. Okay, so that already is indicating that the payment is less frequent than the interest period and the interest compound. For Josh balance just before his ninth contribution by the finding the annual effective interest rate and check your answer using 4.2.8. So, and you can see the solutions already written here. The 3,000 is being multiplied by the is being multiplied by S. This is a new to-do, so there's those two little dot there. We're trying to find its future value because we're trying to find the balance before his ninth contribution. That means he hasn't made the ninth contribution yet, so the total number payment is 8. And we got to find the interest rate for the annual interest rate I. So that will allow us to do the calculation. Now, what is the I exactly? The I is supposed to, the payment is annually. So we need to find the annual interest rate. And over here, if it's the interest period is monthly, so the 4.8 is a nominal interest rate. So the 4.8% has to be divided by 12 to get a monthly interest rate, plus 1, and then raised to power 12 and minus 1 to get the gross fraction. The accumulation is the power 12. You minus 1 to find the interest. So I is being calculated this way. Using that, you will be able to calculate the total future value. That is a 29,953.3. So this is applying what we've learned in chapter 3. Now, in the bottom part, we're looking at using the formula that we learned in chapter 4. That is, we're calculating annuity due. So the denominator should be AK. The numerator should be SN. In this case, the SN should be number of interest period. If we have a monthly interest rate, every year there's 12 interest period, and we're talking about 8 year before the ninth contribution. That will be only 8 year before the beginning of ninth year. So the ninth year is not here yet. Beginning of ninth year. So 8 year, 8 times 12 is 96. So there's 96 interest compound period. The interest rate is, it's a monthly interest rate, so it's going to be 0.04004. That is 0.048 divided by 12. That's how you have the interest rate. On the other hand, in the denominator, we're looking at the K. K is the payment period, and in each year there are 12 period, 12 interest period. So K equal to 12. So in the denominator is A12I. And using this, you'll be able to find exactly the same thing. The calculation S96 0.004 over A12 0.04 times 3,000, the final answer will be 29,953.3. So that echoes the idea that using the method that we have in chapter 4, the SN over AK, we're able to calculate the same thing that we would be able to calculate using chapter 3. That is this. Okay, you can also use BA2 plus calculator to do the calculation, and you can use both ways. So this is the thing that you have to key in. Number 1, since the question is talking about annuity due at the beginning of the year payment, so we would we first have to set the calculator in begin mode, and you know how to change the mode, I hope, and then set the PY payment per year as 1 because it's an annual payment, and then you're gonna set the interest rate per year as 12 because it's a monthly interest rate. It's convertible monthly. The interest rate is being compounded every month. So CY is 12. So we're going to click second P/Y1, enter. So that sets the PY equal to 1. And then next you enter 12 as your CY equal to 12. And then enter. So that finished setting this too. and then second quit. So that finished setting part. And then we're keying the rest of the information. You put n 8 equal n equal to 8n, and then you put in the interest rate per year as 4.8 as per this question. 4.8 interest rate compound monthly, and you put in 0 present value of 0. That is because we are trying to calculate future value. So we're taking it out as a negative future value because all the payment is being considered. Right, we considered, let's see, the cash flow. So you're making contributions. So this is a cash outflow for you, and your future value is positive because that's your money after you put it in. Okay, so if we put in 3,000, negative 3,000, the way we put in negative 3,000 is to do 3000 and then negative, and then payment. So that set up a payment amount being negative 3,000. The payment amount is 1 per year because we already set p slash y equal to 1. And then we will calculate CPT is compute, and then we're going to compute future value. After you finish, we'll follow this progression of the code. You get future value, the output the calculator going to display future value equal to 29,953.297, and that's how we get this calculated using the BA2 Plus calculator. Most of the question in this structure comes, well, fluently using the BA2 Plus calculator. All right, and let's try to devise the similar formula for perpetuity. Let's just say we have a perpetuity, the present value can be calculated using A infinity I. According to the formula in chapter 3, in A infinity I equal to 1 over I. This is using the geometric theory that summation of the geometric theory that we learn in calculus. All right, what is I exactly? I is assuming that the interest payment is K interest period. So K is how many interest period involved in each payment period. So then the I has to be calculated by 1 plus I to the power K minus 1. Right, and then that, if you divide it by I, that's the SK formula. That echo the formula we learned in chapter 3. So it's 1 over I times SK. And that is similar to, so remember if you have annuity immediate, remember it was it was AN over SK. Now 1 over I is also AN if can't really see AN here. A infinity. So in this case, 4.2.10 is actually A infinity with lowercase I over SKI, since the payment period is finite, but for perpetuity, the number of payments is actually infinity. All right, so for annuity immediate, it echoes what we learned before. If you are calculating annuity due, then it echoes the one, you will switch the SK in the denominator to an AK in the denominator. Everything else will be the same. The logic is similar. Okay, so this gives us a way to handle a new perpetuity calculation of the value of and for perpetuity, all we are calculating is present value. Since a future time point is infinity, we won't be able to calculate future value. All we are calculating is present value since it's perpetuity. All right, so let's look at example. Here we have a perpetuity paying 1,650 at the end of each year is to be replaced by another paying X dollar at the beginning of each 2 year. So if you think of it, this is 2 perpetuity gotta have the same present value. I think the present value of each perpetuity is 31,250. We want to find the X. And you can see the I is not given, so I guess we don't know the payment X. We also do not know the interest rate, but we can use the value of the perpetuity, the 31,250, to identify the interest first. Okay, that's what we're doing. Since the present value of the first annuity is 31,250 and the each payment is 1650, that is giving us the first equation that we are able to solve for the I. If it's a perpetuity, then the I is equal to, this is our interest rate. And these two, we're assuming they are following the same interest rate. So for the second question, paying X dollar at the beginning of each 2 year. Okay, so the interest rate, the 0.0528 is an annual interest rate. That means your interest period is 1 year, but your payment period is 2 years. That still goes with the idea of this section saying the payment is less frequently than the interest period. So with that, we have the denominator gotta be the payment period interest rate. So that's 1 plus I to the power 2 minus 1. And the numerator is supposed to be another pay X at the beginning of each year. So this will be the present value 3120 is equal to, and it goes with this formula. It's annuity immediate, so you will have every 2 year. I see. X dollar that takes a place of 1650 that replaces 165. The amount of payment is X dollar, and then the interest for the 2-year interest is 1 plus I to the power 2 minus 1. Numerator is because we're switching from the end of each year to the beginning of each 2 year. So, and you can see the timeline. Instead of paying 1650 every end of the year, we're paying X at time 0 and X at time 2 and X at time 4. So we have to multiply the 1 plus I to the power 2 just to get to the value of, why is it not dividing instead of multiplying? All right, we can think of it. If you do not multiply the 1 plus I square, the green 1 plus I square in the numerator, you'll be calculating X dollar paying at the end of every 2 years. But we are actually paying at the beginning of every 2 years. So that equalizes that the payment is, the actual payment is X times 1 plus I square. That will be the time 2 value of the payment at time 0. I hope that kind of makes sense. All right. You can also understand it, follow the formula of 4.2.11. This is a present value of the perpetuity paying at the beginning of each K interest period. And then the I has to be the interest rate for one interest period. All right. Let's see, is the time? Well, I'll try read through chapter. We still have time. Then we can go through another section. 4.3 is a different perspective. In 4.2, the payment is less frequent than the interest period. In 4.3, we're talking about payment more frequent than the interest period, right? Either way, they're not coincide. If they're coincide, it will be the same as chapter 3. So we're saying that, for example, if you compound annually, but then you're making a monthly payment, then how do we handle the present value and future value of the annuity, that kind of thing. All right, so let's look at an example just to derive the formula. So this example saying math P was offered a scholarship with level monthly payment. So here the payment is monthly for 4 years. The first payment would be made on September 30, 2000, and each year the payment would total 5,904. And to fellowship. So we're comparing to one is the scholarship that has a monthly payment, and the other one is a fellowship by another college. The later would pay 5,000. Each year the payment would total 5,904. But the payment actually is not monthly, not the yearly total. Okay. The second scholarship is 5,800 on September 1st of 2000. So the second payment is making an annual payment of 5,800, assuming the gross of money is governed by compound interest at annual effective rate of 4%. Annual interest rate is 4%. And compare the value of the two grants. So both of them gotta have the same annual interest rate of 4%. And we're trying to compare the two scholarships. Are we comparing the present value or the future value? I guess it's the same. All right, so let's look at the differences between the two. The first one, the total is, I actually have two different formula at the bottom. The 5,900, the 5,904 divided by 12. That's the amount of each payment. It's a monthly payment. So if you are being paid monthly for 4 years, the total payment is 48. And we gotta find the monthly interest rate over here because the payment is paying monthly. We have to convert the annual interest rate of 4% into an annual interest rate. That can be done. It's like 1 plus IM to the power of 12 equal to 1 plus annual interest rate of 0.04. So the IM is 1.04 to the power of 1 over 12 minus 1. And that is what we're applying in the bottom left formula. That come out as a present value of 21,821.02. The second fellowship, the fellowship is paying annually 5,800. There are 4 payments because there are 4 different years. And interest rate is 4%. That is the one that we can use directly with annuity formula, but it's being paid at the beginning of the year instead of at the end of the month as the first scholarship. So this is an annuity immediate. Using annuity in immediate formula, we come up with this. All right, so that is the that we can look at the two. It looks like the second scholarship has a slightly more value. All right, but what we're trying to get from here is from the bottom left in the calculation of IM, if we compile that into the formula for A48 and IM, that part is really the present value calculation for annuity that pays more frequently than the interest period. So utilize that, we come up with this formula. This is when the number payment is more than the number of interest period. So the calculation what we're using here, ignoring the 5,904, so it's 1 over 12, and this is going to be 1 over m being the number payment per interest period. Okay, and then here we have A48. How do we get the 48? 4 times 12. And the 4 is number of year, and then which will be and then the 12 will be the number of payment. So 4 times 12 is n. We're using n to represent number of years, number of interest period. N represent number payment per interest period. So N times M is total number of payment. That is, the capital J is representing the IM here. I guess that's the same as IM. All right, so this is the present value formula. It pays 1 over M at the end of each M's interest period for a total of 1 per interest period. The J is representing here, and then where the J matches the IM that we had in this example. So we're trying to get the idea from an example. As you can see, many of these questions, you can calculate the solution without applying the formula. The purpose of these formula is it's making things more clear and also make the solution more concise. But if it's being it become a burden for you to memorize too many formula, there's two ways to handle this. Number one, you find the connection between the formula, and then that's in the end making remember the formula not as difficult. Two, if you refuse to remember or try to research the connection between different formulas, is that you go back to the fundamental connection using the formula we already have in chapter 3 and solve all these. Okay, so it looks like if we want to streamline the calculation, we're gonna look at how to represent the things with a easier notation, and that's what we're talking about. So in this case, the N represent the interest period, number of interest period, as what it is in the last section. M represent number payment per interest period. Okay, so the number payment is $1 per interest period, but then you're being paid more frequently. So it's 1 over M per payment period. And so right here, you can see the timeline is time 0, then time 1, then time 2, and then time n. So this is a timeline. Top one is the number payment and value of the payment. We are being paid 1 over m each time. So the total number payment per interest period is $1 in this case. With that, we have the present value, we use A and M, and future value is use S and M, and still represent number of interest period. That kind of echo with what our previous notation, so they don't conflict each other. And then the N is representing, the M is representing number payment per interest period. Okay, so with that, we come up with this formula. The ANIM is equal to 1 over M ANMJ, which is what we were mentioning in the example before. SNI is 1 over M SNMJ, and J is the interest rate per payment period. It actually should be a smaller interest compared to the I. So even though we have lowercase I and capital J, but J is actually smaller than I. Okay, with that, you can see the formula for this AN is a present value calculation. The payment is 1 over M, and then the V is discount factor per payment period. Using the formula that we had before, we're able to derive a formula for 4.36 and 4.37. They're both the present value and future value for this annuity that has more frequent payment than the interest period. Actually, personal experience, I use the chapter 3 formula more often than the chapter 4 formula. But either one is okay. All right, let's try this. You can try both ways. Your old way, your previous experience or the new way. In this question, we have Shirley invested 2,000 at the end of each quarter for 8 years. So that means there are 4 payment of 200 per year for 8 years. 4 times 8 is 32. So there's 32 payments having annual effective interest rate 4%. So you can see the interest rate period is 1 year, but the payment is quarterly. So this echoes the idea that the payment is more frequent than the interest period. Find Shirley's accumulated value. Accumulated value means the future value at the end of her last deposit. This is end of the period, end of the payment period payment. So we're trying to find the future value. With this, there are 2 ways to do the calculation, and you can see the way I calculated, I did the previous formula. So there's 32 payments, so I did A32. But if we're doing that way, you gotta calculate the IQ, that is a quarterly interest rate. So the quarterly interest rate is 1 plus IQ, assuming that IQ is what we're solving, to the power 4, which equal to the annual interest rate of 4%, so that equal to 1.04. Solving IQ from here, IQ is 1.04 to the power of 1 fourth minus 1, that's IQ. And that allows you to get the future value calculation. We get 7481. So the red solution is utilizing the formula that we had in chapter 3. If you're doing it this way, you have this extra task to calculate that you got to calculate IQ, the quarterly interest rate, before you're able to calculate the total future value. And that actually is a present value, isn't it? And we were supposed to calculate its future value. Yeah, what's our problem? I should turn that A32 to S32. If we're doing A32, that definitely is a present value calculation. So notation should switch. All right, the green one is actually utilizing what we're talking about using the formula here, the 4.3.7 indicated if you want to calculate the cumulative value Sm, if the payment is M, so we're doing S, how many year? 8 years. So supposed to S8 4, parenthesis 4, meaning that there are 4 payments per year. So so for this calculation, you're gonna do you have to have 1 over M, right? M payment, 1 over M S and MJ. Okay, so that's what we're doing. The 800 is divided by 4, so each payment is 200. And then the S84 is, we got a formula here. S84 is 1 plus IN minus 1 over the IM. And then the 1 plus I to the power n minus 1 and 1 plus I to the power 1 fourth minus 1. The numerator and denominator in the second part of the green calculation is giving us this. So since they got the same, I assume, I think their calculation, they're both future value calculation. So the only mistake I have here is the A32 should be S32 there. We're calculating the future value, the cumulative value. Over here on the bottom right, that was a formula for S and M. It equal to 1 over M, S and MJ, and then it equal to 1 plus IM minus 1 over IM. That is the same formula that you see in the last example over here. I hope it kind of makes sense. And that is, yeah. One more thing is you can calculate the same thing with your BA2 plus calculator. What you're going to do, you make sure that the number of payment per year equal to 4 and the number of interest period per year equal to 1. To set those two, we're using the TVM worksheet on the BA2 plus calculator. You enter 200, negative 200 as your payment amount, n equal to 32, n is the number of payment. We got 32 payment of 200, and then the interest per year is 4 because it's 4%. Present value equal to 0, and then we calculate future value. That's giving us the same value that we have here. Practices, you kind of see the benefit of using the BA2 plus calculator. It allows you to enter payment per year and interest period per year easily, so that differences of the two become natural on that calculator, and we don't even have to write down so many formula there. So that is something that takes practice. The more practice question you do behind the chapter, the more likely you start figuring them out. That is 4.2 and 4.3. I don't think I did a lot of PowerPoint on the other three sections, but try it out yourself. I believe most of them can be calculated by devising your own way and match what we're talking about in chapter 3. All right, that is a really short example, really short explanation on chapter 4. I don't know how helpful that is, but please go through your own reading and exercise. If you got any question or difficulty with the example or the homework, please let me know. I did not find matching question on WebWork, so I have to assign homework for this chapter. I assigned the textbook question as the homework question. All right, again, please let me know if you got any question. I'll make short videos or send text explanation through email if you got questions. Thank you.